All right, number 46. A solution of magnesium chloride is 0.850% mass over volume. I'll explain this in a second. How many grams of magnesium chloride are there in 1.5 liters of that solution? Okay, so we in class, so M over V, this is a way of doing a concentration very similar to molarity. And you know, percent mass by volume is a pretty common way to express a concentration of a solution, but it's just something we just didn't do this. But it's very easy. You'll see here. So basically, M over V, like you see here. This is mass over volume, and the units must be grams over milliliters. So like this 1.5 that you see in the problem, that ultimately is going to have to be converted into milliliters for our volume. So anyway, the reason that I'm not keen on this is because it's essentially incorrect to have an amount of grams and an amount of milliliters, because those are different. I mean, they're different units. I mean, they're different things. I mean, and that's really tough to make a percentage out of. But nonetheless, you'll see it. So let's figure this out. So basically, remember that a percentage is like a number over another number times 100. So we're going to say that here. So basically, what they are telling us. So this is your setup, basically. So we're trying to figure out this value here, and we're going to use this because we've essentially got that and we've got that, and so we're just going to use those two numbers to solve for grams. So here's what it looks like. They're basically saying that you've got some amount of grams of magnesium chloride divided by a solution volume of 1.5 liters. Now, I told you that had to be converted into milliliters. We just multiply by 1,000, and that is 1,500 milliliters. And I'll kind of longhand this out for a second here, but basically, to get a percentage, you'd have to do this division, then multiply that, what is going to be a decimal, by 100, and that is going to give you a percent, which in this case we've been given as 0.850%. So I'm going to actually put that in here, 0.850. Okay. Now, to do this, I think more effectively, let's get rid of this times 100, because ideally I'd like to have this set up where we just have grams over milliliters equals the percent. But we're gonna essentially turn our percent back into just a decimal, and we do that by just instead of multiplying this by 100, we're going to divide everything by 100. So 0.850 divided by 100 gives us 0.085. So now our setup is this: grams of magnesium chloride over 1,500 milliliters equals 0.0085. Okay, so I mean, really, this number we would just multiply by 100 to get that percentage, but we don't want the percent. We want this decimal value. And now it becomes really easy to solve for our numerator, because all we have to do is multiply these two numbers, and that will give us our final answer. So that's already on the calculator, times 1,500. That gives us 12.75, and that's our answer. Now, in this case, you know, don't be like thrown off by it being magnesium chloride. It could have been any compound here, because we're just solving for the number of grams of really any solute that you're going to use. Yeah, that's how you approach that problem. That's how you do it. Okay, just make sure your liters are converted into milliliters. Okay, all righty. Where's the next? Oh, there it is. Okay, let's finish this thing up. Number 47. Okay, another alpha decay radiation problem here. Remember that emitting an alpha particle, which looks like either helium with a 4 and a 2 or the alpha symbol with a 4 and a 2, causes the resulting atom to have 2 fewer protons and an overall mass decrease by 4. And we actually did a problem like that, right, earlier, but let's focus on this one. If an iodine 126 isotope emits an alpha particle, the resulting atom is, well, I mean, we've got everything we need, but let's actually pencil this out. So iodine 126 looks like this. The symbol I, 126 is the mass, and iodine's atomic number from the periodic table is 53. Okay, so this is going to emit an alpha particle, which is 4 and 2, plus some other, atom is going to be in that box right there. So remember, this is just a numbers game. The 2 and the whatever that number is going to be have to add up to 53. So what plus 2 gives us 53? 51, right? And then this number here, plus 4, is going to give us 126. So what plus 4 gives 126? 122. Okay? So, and then remember that 51, that is the number that we're looking for on the periodic table to give us our symbol. And 51 is Sb, that's antimony. So the symbol is Sb, 51 and 122. Okay, that's your answer. Okay, 48. What is the equilibrium constant? Okay, so you're going to be expressing the equilibrium constant for this reaction. And a couple of things to remember. We always want to have, we want to have the products over the reactants. And we basically said we have like A, B, B, in this case C, C, and D, D, where the little number is the coefficient, and then the big letter is representing the chemical formula in general. Okay, so the other thing to remember is that water is not going to be included in an expression for a equilibrium constant. So what we're looking to do ultimately here is put like C, big C raised to the power of little c times big D raised to the power of that. And then we would have A raised to the power of A multiplied by B raised to the power of B. Okay. Now in this case, we're only going to have, we're not going to have this value for B because it's water. We leave water out of this. So the expression here is just simply, going to put our C3OH. Oh, whoops, CH3, I thought that looked weird. C3OH raised to the power of 2 multiplied by H2. Now, this hydrogen does not get a coefficient, hydrogen does not get what is the number I'm looking for here? Exponent. Hydrogen doesn't get an exponent because it doesn't have a coefficient. Okay, and then the only thing we're going to have below here is the CH3 raised to the power of 2 because 2 is the coefficient, right? So that is your expression. Leave water out. You know, unless water is built in somehow to the formula, like sometimes you see like water by itself you leave out all the time. But if it's like this, like CuSO4, you might see this actually times like H2O. If you have a formula that is like got some inclusion of water within the formula, then you don't like omit that from your expression of your equilibrium constant. And this is called a hydrate, and you may see that. You may or may not. I gave you one of these as a bonus on your Unit 7 test. Anyway, if water is part of the formula, leave it. It'll stay as part of your expression. All right, number 49. In a reversible reaction, the equilibrium constant is always a very big number or a very small number. We talked about this in class. Big is anything over 1 and small is anything under 1. Big equilibrium constant mean that the forward reaction is favored and there'll be much more product than reactant. Small means the opposite of that. I think it's possible I told you this wrong in class, but hopefully by the time you get here, we will have already remedied that mistake that I may have made in class. So here's the deal. KEQ, if it's greater than 1, that means that the forward reaction is favored, and that means that we will have more product than reactant. If the KEQ is less than 1, then we're going to have, it favors the backwards reaction, and we're going to have more reactant than product. Okay, so we're looking for numbers over 1 or under 1, essentially. So this is just saying, basically in this example, in this reversible reaction that we've got set up here with these imaginary chemicals, if the equilibrium constant is 2.1 times 10 to the 4th, that is a very big number, certainly greater than 1, right? That means that we are favoring the forward reaction, which means we're going to make a bunch more product and not have as much reactant. This is big KEQs are the ones that drive the forward reaction. So we are going to have more product. Boom. All right, last one. In a reversible reaction where all the chemicals are gases, another stress to equilibrium is a change to the volume or a change to the pressure. And those two things go hand in hand. When you like the way that you would change the pressure of a system like this is usually by adjusting the volume in which that takes place. And just remember the relationship. If the volume is going up, that means that the pressure is decreasing. So we increase and decrease pressure by increasing or decreasing volume. And the opposite would be true here. If volume goes down, then pressure goes up, right? So this just says increasing the pressure by decreasing the volume causes a stress to occur on the side of the equation with more moles. More moles. Here is a good example of that. Like here's an equation. This is a really good equation to show you this with. Here on the reactant side, we have 4 moles, right? There's a 1 in front of that N2, and over here we only have 2. And so if we were to increase the pressure at the where this reversible reaction is taking place, we would stress the side with more moles. That would take our equilibrium from being balanced at equilibrium to being stressed on the reactant side, which would drive the reaction forward. And that's kind of what this next part of this question is asking you. This just says if the volume was decreased, meaning that the pressure is increased, the result would be, well, it's this we just talked about. We're stressing the side with more moles. So our equilibrium constant, or our equilibrium is stressed on the reactant side, which means we are going to essentially push the forward reaction. That means a shift to the right. Now, do not fall for the idea that we are going to increase or decrease our equilibrium constant KEQ, that is. Changes to pressure do not change the equilibrium constant. The equilibrium constant can only really be changed by temperature. That's why there was a former question that said, what is the best way to drive a forward reaction, and that's to heat it up essentially. But a change to the pressure does not do that. It does not increase the equilibrium constant or decrease it. So the only right answer here is A. We are going to shift to the right, which means we are going to favor the production of our products to reestablish equilibrium. Okay? Good.